Good evening, everyone. My name is Ware Harmon, and I'm the Executive Director of Town Hall Seattle. On behalf of our team and our friends at Third Place Books, it's a pleasure to welcome you to tonight's virtual presentation of Dr. Nir Barzilai, Conversation with Dr. Lee Hood, co-produced with our friends at the Institute for Systems Biology. I just realized that's a lot of friends on board tonight, but they are all friends. Friends, everyone. As we get underway, I want to acknowledge that our institution stands on the unceded traditional territory of the Coast Salish people, and particularly the Duwamish. We thank them for our continuing use of the natural resources of their ancestral homeland. We're very glad you've joined us for this evening's program, virtually. Unlike some programs now, which are happening live in the building or being offered in a hybrid format, which means obviously in the building and online, tonight's audience is all virtual, and the program will run around 50 to 60 minutes, including Q&A. We have a new Q&A platform this year to better integrate our in-person and virtual audience experiences. And so to submit your question, please enter meet.ps/Barzilai or scan the QR code right now on the screen with your smartphone. We'll drop this link in the chat and remind you later how you can get to the Q&A and how you can use that link. We can't guarantee we'll be able to address every question, by the way, but we'll try to get to as many as possible. And for those who want to view the program with closed captions, please click the CC button in the bottom right corner of the video player. Town Hall's adding new events and podcasts every day. Upcoming programs include an autobiography of plastic as a cultural and environmental force. I guess you could say it's ghost-written by Allison Cobb. Thor Hansen's look at animal adaptations to climate change, Bill Schutt's Natural History of the Heart, and upcoming programs featuring Susan Orlean, David K. Johnston, and Neil Stevenson, among many, many more. Please visit our website to join our email list and get the latest updates as more programs are added throughout the season. The Institute for Systems Biology, our co-producers tonight, are a nonprofit research institution located here in Seattle, dedicated to the study of relationships and interactions between various parts of biological systems and to advocating for an interdisciplinary approach to biological research. I want to thank the ISB team, and in particular President Jim Heath, for their long collaboration. I was thinking about this, it's got to be over a decade now, begun back in Dr. Hood's tenure, and so we're extremely grateful to ISB for helping us bring timely, high-level conversations about the cutting edge of medicine and medical possibility to town hall audiences and well beyond. Town Hall's work is made possible through your support and the support of our sponsors. Our Arno G. Matulski Science Lecture Series is supported by Microsoft and the Wincode Foundation Northwest, but as most of you know, Town Hall is at heart a member-supported organization, and I want to thank all of our members watching tonight. If you share in Town Hall's vision of a community energized and empowered through considering questions of politics, science, and culture, please support us by becoming a member. There's information about that on our website too. Finally, you will definitely want to dive deeper into this evening's topic by purchasing your copy of Dr. Barzilai's book. And the most expeditious way to do that, I promise you, is the link in the chat below, which will take you directly to our good friends at Third Place Books. And with all that, Dr. Nir Barzilai is the founding director of the Institute for Aging Research at Albert Einstein College of Medicine at Yeshiva University. He's also the director of the Nathan Schock Center for Excellence in the Basic Biology of Aging. He serves as the scientific director of the American Federation for Aging Research and directs the Longevity Genes Project, a genetics study of over 600 families of centenarians and their children. In addition to his longevity gene research, Dr. Barzilai studies key mechanisms involved in the biology of aging, including how nutrients and genetics influence lifespan, and he is the co-founder of biotechnology company Cobar Incorporated, where treatments for age-related diseases are being developed based on Dr. Barzilai's work. In 2000, Lee Hood co-founded Seattle's Institute for Systems Biology, ISB for short. He served as its first president from 2000 to 2017, and he remains with the Institute as professor and chief strategy officer. When ISB affiliated with Providence in 2016, Dr. Hood became Providence's senior vice president and chief science officer. He's currently carrying out studies in Alzheimer's disease, cancer, and wellness while pioneering a 1 million patient genome and phenome project for Providence. Dr. Barzilai's book, Age Later, Health Span, Lifespan, and the New Science of Longevity, is the subject of their discussion this evening. Please join me in welcoming Dr. Lee Hood and Dr. Nir Barzilai.
Nir, thank you. Weir, thank you very much for that wonderful introduction. It's a pleasure to be here with Nir today, one of the outstanding researchers in aging. And I will say aging is one of the hot topics in biology today. So I think our listeners would really be interested. How did you get interested in aging in the beginning, Nir?
Well, first of all, in the beginning here, let me thank you for having me. This is a great program, what you're putting together, a great effort. I hope it spreads around, and I'm just excited to be here. Also, before answering your question, Lee, and by the way, Lee, you're a pioneer on your own right, and you've done really incredible things. So it's an honor for me to be with you too. And just before answering the question, I want to say one sentence, and that is, you know that aging has a biology because you know who's old and who's young. What people didn't realize that this biology is driving diseases. Okay, it's not the diseases cause us to age; it's the aging causes the disease. But more important, this biology of aging is modifiable. You can target this biology and you can extend both health span and lifespan. So this is a message. If you don't accept this message, you have to leave first class now and go to coach, okay? But this is where I want to start. Okay, and now you're asking, where did I start, right?
Right.
And I think, they say that kids have imagination, which they do, but I don't think that most kids look at their grandparents and think that they're going to look the same. I think they're more thinking, how did they get here? And I realized when I was about 13 years old, I was walking with my grandfather and he was telling his life story. And he wasn't that old. He actually was my age. He looked like 20 years older than what I look now. He was bald, but with white hair around, and he was obese and he was slow. And he was telling me about all those things that he has done. And it just didn't make sense for me. And through that day, I always thought I wanted to be a doctor, but I always thought, aren't you missing the point? You're talking about cholesterol and hypertension, but there's something much more dramatic that happens here. And it happens with aging. So I really wanted, for a large part of my time, to understand this biology of aging. I thought it's a bigger problem and it's very interesting. And maybe there is a hope.
So how did you get started with your aging career then?
So look, I was looking for a mentor, okay? But when you're looking for a mentor in a field that doesn't exist, you decide to go and train in a field that exists and it's relevant. And this is endocrinology, okay? We know that all those hormones are changing. And I thought that's a good start, because maybe it's all hormones. The hormones are going down, some are going up, but if we just fix that, we're going to fix aging. Big mistake. But nevertheless, I got really expertise in metabolism, and I'm a diabetologist. Today I've seen patients in the morning. I'm seeing patients from time to time. And this expertise actually helped me to get into aging from the hallmark of metabolism. And then I started developing with the other people who came like me to the field.
Wonderful. So what was the first really interesting aging experiment that you did then?
Well, so when I started a lab. I was really more a physiologist that was trying to understand biology. And I was then very impressed with the fact that humans are developing obesity And in particular, it became apparent, by the way, lots of people in Seattle did the clinical work on that, that it's central obesity, it's the abdominal obesity, it's the obesity where old people sometimes look pregnant. It's the fat inside the abdomen that was center of this metabolic abnormality or this insulin resistance or this metabolic syndrome of aging. It has many names. And what I've done in the lab, the first really cool experiment that I've done is I took rats and aged them, but for some, I took their intra-abdominal fat, this abdominal fat out, and basically looked what happened to the metabolism and what happened to their lifespan. And I showed that rats, that you take their abdominal fat out, only the abdominal fat, live healthier and live longer than other rats. So that was a cool experiment because it was a surgical removal. That's all I've done.
Did the fat return quickly or did it stay low for a long time?
Well, that's a good question. We did many models and we discovered that you have to extract the fat sometime after puberty, because if you do it during puberty, it regrows within few months. So you have to let them grow fat, and then take it out, and then it really doesn't come back. In the models where we took fat early, we prevented diabetes in some models, but then a few months later, all the rats developed diabetes. When we opened them up, we saw that this fat returned. So we needed to go away from where the fat returned and do it at the right time.
Right. Now, you're famous for having looked at 500 centenarians and their families. And I wonder, what was the rationale that initially set you on that trajectory?
Yeah, 750 centenarians and their families. And we're now trying to get 10,000. It's another story because we're finding so many longevity genes there. But this is really simply the story. You guys in Seattle have an incredible investigator that's called George Martin, who's actually the father of the biology of aging. And he actually looked at models that live short. We call them progeria. It's diseases that are called progeric diseases. There are several of them, and they happen in humans. And those kids are really aging rapidly and dying in a very young age. So that was one way to look at aging. And as he was making progress in those studies, other investigators have shown in a simple animal like a nematode that if you modulate one gene, you can have an extension of lifespan. 2 times, 3 times more lifespan. One gene really controlled basically aging and longevity. And that was the major breakthrough in our field because all of us started to look at animals that live longer. And maybe you don't learn everything you have to learn about aging, but you start having some ideas of the mechanisms that are involved in aging. So I had a lab with the rats, but I'm also an MD. And I said, well, who's living longer? Centenarians are living longer than anyone, right? It's true, it's rare, but 1 out of 10,000 at the time I started lived to be 100, which basically doubled the life expectancy of their friends. When I started this study and the people were born between 1900 to 1910 or between 1900 to 1920, life expectancy at that time was 40. And if you got to 40, it became 60, but they're 100 years old. So they pretty much doubled their lifespan. So this is quite impressive. And the question was, do they have longevity genes that allow them basically to slow aging and to get to this age? And if we can find a mechanism, maybe we can imitate it in all of us.
So what observations came from these studies then that were significant?
So first of all, the first thing that was important to note is to see, did they become sick when everybody became sick? And all they're doing is they live sick longer? Or is their health span and lifespan, does it go together? And it does, okay? Those centenarians had 20, 30 years more of health span than control that were really the age of their kids, you know, a current control. So it's not only that they live longer, they live healthier. But there's even much more important thing. We start having diseases 5, 8 years before the end of our life. And, you know, we carry those diseases, we accumulate those diseases. In fact, after the age of 60, you get one disease and then the second disease and one treatment and another treatment, and the treatments are antagonistic and the diseases are terrible. We shouldn't do it anymore, and we don't have to do it anymore. But the centenarians had a very short time of disease at the end of their lives. We call it a contraction of morbidity. They, you know, 30% of them just don't wake up in the morning, but they get diseases for weeks or maybe months before they die, not like the rest of us. In fact, the CDC have looked at the medical cost in the last 2 years of life. Somebody who dies after the age of 100, or those who die, you know, at 70, and it's third the cost. I mean, even the CDC documented since 1993 that centenarians, the medical cost is very low. And by the way, when they were 70, they even didn't go to their doctors, okay, because it wasn't part of what they did. And so the medical cost throughout their life was really very low. So we want to imitate that.
Yeah. So this contraction of morbidity, do we have any idea about mechanisms that cause that? Because that's a remarkable way to die.
So, you know, in the biology of aging, we, and when I say we, is my wonderful colleagues, we agree that there are 9 hallmarks for aging. You know, some of us put it in 7 columns and some of us in 9, but we kind of agree on those hallmarks of aging. How do you become a hallmark of aging? Well, you have to show that something goes bad as you age or change as you age. And when you fix it in animal models, they live healthier and they live longer. That's how you become a hallmark. Not only that, you don't have to treat all the hallmarks to make progress. You can treat one hallmark and affect the others too. It's really, if you take an old cell or an old organ or an old body and make it young, many things are being repaired that way. Mm-hmm. So those hallmarks are interconnected, and this is basically our view into aging. This is also the investors' view out of aging, because there's a huge biotech wave, $4.5 billion investment in biotechs that are for longevity now,
right?
Because we kind of framed this biology of aging.
Now, you discovered the first longevity gene. What exactly is the longevity gene?
Well, so the first one that we've discovered was interesting story in the sense that we saw that a lot of our centenarians and their children had very high level of the good cholesterol. It's also known as the HDL cholesterol, or the high density lipoprotein. And so early on, when the genetic methods were not that great, we looked for the genes that we thought are modulating this HDL cholesterol. And we found actually two genotypes, that one goes from about 5% to 15% in centenarian. Okay, so if we see genotype that's going up, it means that those survived. That's why you have more, because it allowed them to survive. And so this was in a gene that's called CETP. And there's another mutation in the promoter of another gene that's called ApoC3. And the interesting thing about that is that we presented this data, and two pharmaceuticals have developed drugs. And I think that's important for our audience to know. The fact that we're finding genes doesn't mean that we need a genetic treatment, okay? The genes are just the mechanisms. And once you know the genes, and once you understand the function of the genes, and once you know if you have to inhibit it or to accelerate it, then you can develop a drug. So Merck developed a drug, and Ionis developed a drug, and there are two drugs that are there, but they're there for managing lipids, okay, cholesterol, but not aging. But what the pharmaceuticals saw, what they realized, if a lot of centenarians have those mutations, so if we develop the right drug, it's safe, okay? You always want to find with genetics if maybe you're doing the wrong thing or the opposite thing. And so if you can see the safety issue there, that's an advantage. So this is an example of how we contributed already to drug development.
So if you had to pick out one or two major things that came from the centenarian studies, what would you choose?
So I think the best story that we're I don't want to say completing, but it's very important for theories of aging, and it's very important for clinical practice. And I'll say what it is, and then I'll explain what we found. We found that there are functional mutations in the growth hormones. There's not only one growth hormone, but in growth hormones in centenarians. In other words, the growth is not well activated as in other people. Now, it's interesting because in nature, the dwarf, the little, live longer. You know, the small dogs live longer, right, and the ponies live longer than the thoroughbred. And when you mutate in the lab or you find dwarf models, they always live longer. And I actually thought, okay, good for them, but I don't think that's good for humans. And it's one of those grants, you know, most of the grants that I wrote, my hypothesis, I could disprove my hypothesis. This is an hypothesis that I didn't believe, but I proved it to myself. So we looked at all the growth hormone axes. And I think this is the story. In order to understand it, this is the story. There is we are talking in aging about an hypothesis that's called antagonistic pleiotrophy. What is antagonistic pleiotrophy? Something that's good for you when you're young is turning against you when you're old. For example, we need cholesterol. We need a lot of cholesterol to develop our cells, our brains, our gonads, okay? But if cholesterol metabolism is increased after we had our kids, then this cholesterol can cause damage, okay? So good in the young and bad in the old. Growth hormone is pretty much the same. You need the growth to get to reproduction. But when you start the breakdown of aging, okay, you need to change the energy. You don't want to grow. You want to protect the breakdown. And that's why the people who have the lowest growth hormones and those mutations are the one they live longer. And this accounts from for almost 60% of our centenarians.
Mhm.
So it's a
Wow.
major pathway. And I guess I should say the lesson is a lot of people out there, either maliciously or for not knowing, will give growth hormone treatment for elderly. And my story tells you that this is probably dangerous.
It's very dangerous. Yeah.
You have to do the opposite.
Well, I was struck in your book when you said approximately 50% of the centenarians actually were obese, and perhaps slightly less smoked regularly. That seems to defy normal environmental constraints, and more strongly suggests genes have a very important effect.
Right. And I got a bad press that my dean didn't like, because Jay Leno in his time, okay, so we published it when Jay Leno was on in the Tonight Show. He said, well, we just found the secret for longevity. You have to eat a lot, to drink a lot, not to exercise, right? and the point is, for those people, for those centenarians, it really didn't matter, because their aging was slow no matter what. Okay, for the rest of us, it is important. So it's true, 60% of men and 30% of women smoked for a long time. Helen, one of my favorite centenarians, she's actually one of 4 siblings who were all centenarians, 102, 110, 107, 109. I met her first time in a New York apartment, and she opened the door and she was smoking. And I said, Helen, nobody told you to stop smoking? And she said, all 4 doctors that told me to stop smoking, they died. Okay, so if you smoke for 90 years, you live a long life. But the point here is it didn't matter for them, and the obesity didn't matter for them, and the lack of exercise didn't matter for them as a group, right? Some of them didn't smoke, some of them did exercise, but as a group, they didn't, which really helped us to frame the fact that they have longevity genes. And by no way do I remember giving a radio talk somewhere, and I was going to the airport, stopping at a Starbucks, and a young man said, weren't you now on television? And I said, yeah. He said, you changed my life. I said, why? He said, I saw you in the gym, and I thought, God, my grandmother is centenarian. I don't have to exercise anymore. And of course, you do. You do.
Yes. Yeah.
And we're not using it to say not to exercise, but to find why those guys didn't interact with the environment the way we all should, and still got there in pretty good shape.
Yep. Well, I'll tell you 2 things I found very interesting about aging are, one, the mechanisms seem to be highly conserved from a single-celled organism all the way up to man. And what that implied to me is that the master control mechanisms must be relatively simple and able to do very different things in different organisms. And I just wondered about your thoughts on those kinds of ideas.
Yeah, in fact, a lot of investigators in other fields criticize us for using aging models. We said aging models is the platform, that's the biology. If you're studying cancer or cardiovascular disease or diabetes on young animals, you're missing the important interactions.
Yep.
And in fact, the models for those diseases, the model for diabetes is not the diabetes in humans. It's not. Okay. The model of Alzheimer's
is not the Alzheimer's of a human. Absolutely.
Right. You can cure apparently mice with this kind of what they called Alzheimer, but it has been irrelevant for treatment so far. We just published a paper in Nature Aging where we looked at really the difference between the genetic pathways of humans with and without longevity. And what the top pathways that came were exactly the same that we knew from animal. It's the growth hormone insulin pathway, it's the mTOR pathway, it's the MEP kinase pathway. We got exactly the same result, confirming that aging is conserved and that the animals are showing us pretty much a lot of how we can start, how we can realize the promise now.
You know, some have argued that aging is really a disease, and we have means for preventing this disease. Is that a view you share, Nir?
So I'm going to ask you to answer you a little bit in considering the politics, right? The politics happens in health. We see in vaccination, right? So first of all, I do believe that aging, it happens to everyone, but it's not a good thing, okay? We don't like it, and I don't think we should accept it. But this is the problem. Let's say you decide everybody the age of 65 is old, okay? And we call them a disease. He has a disease. She has a disease. You know what? They don't want to hear it, the elderly. First of all, not everybody who's 65 is sick, okay?
Yeah.
And second, you saw after the COVID, you identify those elderly and you were cruel to them, right? You drove them into those islands. They couldn't see anyone. They couldn't interact with anyone. They don't want to be called a disease. The AARP, okay, doesn't want to call aging a disease. The American Federation of Aging Research doesn't want to call aging a disease, et cetera, et cetera. The FDA doesn't want to call aging a disease. What I've discovered by talking with the FDA is we don't need to call aging a disease, because what are we trying to do? We're trying to target aging and prevent age-related diseases. So we call it that. We can say we intervene with aging. The FDA can say whatever it is, but we'll know how to do it. So that's why I'm saying it's a little political. We want all those people with us. We're trying to help them. We don't want to antagonize them, and we don't need to.
So for an ordinary person these days, what advice would you give them on how to avoid aging as much as possible?
So, the obvious thing that takes no prescription is exercise and diet, okay? And I can answer later about exercise, but there's a special thing that we discovered in diet, and that's also from studies that we and others have done. So, by the way, when I told you that we took fat out of those animals and they live longer, we had what's called a positive control. A positive control is caloric restricted animal. When you take a bunch of brothers and you divide them, and half of them get to eat whatever they want and the others get 60% of that, they live 40% longer and much healthier, okay? They actually live healthier, and they kind of die one day, but it's very incredible longevity. And for years, people have used this to say, you should have less for breakfast, lunch, and dinner. But this is not what we've done. What we've done is we would come in the morning and give all the food for the day in the morning. Now, those animals were hungry because they're getting only 60% of what their brothers are getting. So they just finish the food in 20 minutes, and then they're fasting for 23 more hours. So it's not only caloric restriction, it's caloric restriction and fasting. In fact, when we start giving food throughout the day, they are leaner, but they don't live much longer. So that got us all, and most of the geroscientists like me are doing some kind of fasting. I'm doing what's called 16-8 hours. I'm fasting 16 hours after dinner. I'm basically skipping breakfast and not eating, I'm drinking water and coffee without milk and sugar, but nothing to eat 16 hours later, every day. People are doing 24 hours fasting once a week or twice a week. Some people are doing 5 days fasting 3 times a year. There's a lot of variation, but they're all based on the fact that in order to upregulate the mechanisms that protect aging, you have to fast and not only to eat less.
Very good. So there've been a lot of publicity recently about drugs that can affect aging, rapamycin and metformin and so forth. Could you talk a little bit about those and where the studies are that would allow us to seriously consider using them?
Yeah, so first of all, the center of the studies of rapamycin are in Seattle. Matt Caberline is leading a dog study, a very important study. Dogs share our environment. They have electronic medical records. We should use them to kind of get some idea about the drug. So he's doing this dog study and talks about rapamycin a lot. I recommend to have him. But so I'll tell you not about rapamycin, I'll tell you about metformin. So metformin is a drug that's used to treat type 2 diabetes. In fact, it's been in use for more than 70 years. Metformin, or a cousin of it that's called fenformin, were used 80 years ago to prevent flu and malaria and inflammatory diseases. And when they were used, people noted that people with diabetes get lower glucose level. So then it became a diabetic drug. But it really hasn't started in diabetes as a diabetic drug.
Right.
And so years later, because it was a main therapy in diabetes, there's lots and lots of studies on metformin. In fact, some of the studies are what we call clinical studies. Okay, they are controlled with either placebo or another treatment, including thousands of people, including multicentral studies. And basically, they showed that metformin decreased cardiovascular disease, decrease diabetes, decrease Alzheimer's, decrease cancer, and decrease mortality. Okay, lots of studies supporting that. And interestingly, I told you about those hallmarks of aging. Metformin has shown to target all those hallmarks of aging. Again, I don't think it targets the whole hallmarks of aging, but it does something to aging and it fixes many things. And it seems that it targeted all those.
Does it target one of the 3 or 4 master control systems? Or do we know?
Well, we wrote a paper trying to say what's primary and what's secondary, but without evidence. Okay, we all, when you say master, each one of us, I'm not falling in this trap, right? We have 9 hallmark of aging. You ask me who's my favorite. If I had 9 daughters, I wouldn't tell you who's my favorite, right? Because everybody tries to say, really it all starts with telomeres, or it starts with epigenetic, because if we do that and that, we influence the others. Well, yes, every one of them influence the other. You deal with proteostasis, you influence the others. So it's just a comment about master. I'm not falling into this trap, although I believe there's hierarchy. So, metformin, we think that metformin primary action is binding to complex 1 in the mitochondria. Even that's a little bit controversial. And certainly you can get metformin effect not only by that. And that's why people are blaming us that we don't know the mechanism of it. So when that happens, by the way, it happens with rapamycin, when you give a drug and it fixes lots of things and people kind of argue about the mechanism, for me, that means it's aging. Okay, because it fixed so many things. That's okay. That's a drug that's aging. We'll figure out one day how does he do it exactly. But those studies have been done, okay? Each one of those studies has been done, but with one disease, preventing diabetes, preventing cardiovascular disease, preventing Alzheimer, right? So we came to the FDA and we said, we are agnostic to the diseases. It's all aging drives disease. What disease you're going to get next? Well, if your mother is diabetic and you're obese, you're going to get diabetes next. Okay, I don't know what disease you're going to get, but because metformin targets aging, any disease you're going to get, you'll get later. Okay, we'll get 2-3 years of extended health span in a study like that. This is the idea of what we're doing. So we're taking the clusters of those diseases that we're calling aging and which we want to prevent. And this is the study that we're doing for the FDA.
Wonderful. So let's say that all of these drugs and fasting, all of these things worked. Do you have a view about, one, can life be extended beyond, what we've seen to date, 120-ish or so? And can you extend the health span in parallel with extending the lifespan?
Right. So look, for me, this is how I define it. Our maximal lifespan as a species today is about 115 years. Yeah, somebody lived to be 122. You always have some cases like that, but we think it's about 115 years, and we can argue what it is. 100. I like 120 actually, but the point is that we are dying before, half of us are dying before the age of 80. Okay, life expectancy is less than 80. So we have 35 years to realize in a body that has this capacity, right? And that's one challenge. The question is, can we go beyond it? And my answer is not today, but I don't know why we shouldn't look at it. I don't know why we shouldn't start now looking at it in order to just know what's going on and to help maybe getting more years of health as you grow old.
Right, right.
There's no example of a mammalian whose life expectancy was doubled, right, or tripled. So we don't have this proof of concept now. But, I always say, we were talking so far about the compression of morbidity, right? It's the Dorian Day, he didn't age, but when he looked at his mirror, the mirror reflected his age. By the way, that's what I'm doing. I'm looking at the mirror and said, oh, but I'm younger.
Yeah.
So the Dorian Gray is what we were talking about. But there's another scenario. There are two other scenarios. One is the Wolverine, okay? Let's take the old and get them young, or the fountain of youth. Let's take old people, put them somewhere and make them young. This is the hardest thing to do. I think it's much easier to delay aging, to stop
keep
aging,
them young. Yes.
Right, than to reverse aging.
Yeah.
And then there's the Peter Pan, okay? Peter Pan didn't grow old, okay? So think of a treatment that you'll do to people, let's say in their 20s, and they'll get this treatment once a week or once a month or once a year, I don't know, and they'll repeat it. And it will help target a major mechanism of aging. And I think it's possible, if that's happened, you would cross the 115. I don't know for sure, but I think it's likely that if you're youthful, that you'll cross that. Others are arguing about, there's the second law of thermodynamics and the increase in entropy and all that we are limited no matter what, or chemically, physically, we're limited, but it's really a problematic because we are a closed system and we can do a lot of repair. So I don't know how limited.
You know what I think the best argument against that is, Nir? It's something like the Greenland shark, which lives 400 years. Entropy should work equally on any mammal, right? So why do they live 5 times as long as we do, or whatever it is?
I know, and there are many examples like that, and it's actually an important. The comparative biology is a very important part of what people are trying to expand now, and there might be specific lessons from other animals than we can adopt. There's the naked mole rat that lives, like 70, 80 years. And it's actually it's called a rat, but it's more like a mice. But but mice live 2 years. So how come a species kind of same size has dramatic changes in lifespan? This is very important. Why clams live 500 years? The sharks, absolutely. The whales, turtle live 120 years. We always joke, we say because they don't pay mortgage, but still there is a biology, right?
Yeah. Well, look, I'm going to ask you one last question, then I think we better turn to the audience and give them a chance. And that is, from your perspective now, what do you think are the most fruitful directions to explore for aging in the next 10 years?
So again, I'm reluctant to say something favorite. There's a lot of interesting things that are being discovered, including hallmarks. Let me give you an example. Our microbiome is not part of the hallmark, but it's apparent that our microbiome has a huge effect on health, okay? How much we still haven't established, how much is aging, we haven't established. So there's a pipeline to be discovered, and some of this pipeline can be practically turn into drugs relatively fast. So what I'm saying is there's unknown. The second thing is there's lots of innovation in thinking. There's lots of thinking about rejuvenation. Okay, and rejuvenation might be simple, maybe your lymph node can be rejuvenate really very soon. There's lots of things, but of course the challenge is not to leave the brain behind. How do you rejuvenate the brain is a big issue. How can you put new cells and download your memory and your personality so it doesn't change, right? There's huge obstacle ahead, but there are experiments actually to do it. And then there are all those things that are kind of controversial. One of them is hyperbaric oxygen, right? I mean, we thought when we came to the field, we thought oxygen is really dangerous. We're taking antioxidants, right? So to put somebody in pressure of oxygen.
But oxygen for the brain is critical. It's one of the reasons our brain ages is our arteries get harder. We can't transport oxygen as well.
So that's why those guys who are doing hyperbaric oxygen have noticed a major improvement in cognitive function of people. So the oxygen doesn't cause the damage. The oxygen, or maybe it doesn't cause a response, but their theory is that oxygen doesn't get, because of the vascular limitation, oxygen doesn't get to all the cells. And if you put hyperbaric oxygen and oxygen diffuses, it rejuvenates some of the cells in the brain. Right. So I just gave you several more examples of what's coming, and some of them, the hyperbaric oxygen is a business development now. I mean, I'm not telling anybody to do that, and I'm not going to do that, but it is possible that this is a rejuvenating process.
Very good. Well, let's let's go to some of the questions from the audience then. Is there one major thing that makes us age faster, or is just an accumulation of various things?
Yeah, well, I don't want to take the complexity out of aging. But I would say that the major difference for everyone, and you can see it around it, is the exercise and the diet. The people who are obese, look, first of all, in COVID, for example, if you were over the age of 80, you had 200 times more chances of dying than when you're in 20, right? So, and by the way, it just reminded me to say, 9 studies around the world with metformin showing that people on metformin had less hospitalization and much less mortality. In fact, 2/3 less mortality. That's not in my book. That's now coming up. But okay, but back to, sorry, so what point, where did we start? I didn't want to forget something, and then I forgot.
Oh, was there any one thing important about aging, or was it the accumulation of little things?
Right. So yeah. So I said aging is very complex, and diet and exercise have a huge effect on all the hallmarks of aging. Obesity is a major risk for metformin. That's where I started. It is a major risk for COVID and a major risk for other diseases. So if you're not obese and you're exercising, you're more likely to pass the age of 80. Okay.
Yeah.
People on the blue zones that are doing several other things as well have nice longevity, sometimes exceptional longevity. So all those things are important. But think about people who are surviving cancer. They're aging rapidly because we just gave them chemotherapy and radiation.
Right.
They need help. People who have HIV, they get diseases 10 years before their friends.
Yeah.
People who are debilitating. I would say poor people. Poor people cannot get good food and cannot stay. They can buy fatty food and be fat, and they cannot afford to go to the gym. So maybe drug, metformin is cheaper for those guys, for example, than going to the gym or buying food. It's the cheapest drug in the market. And more than that, if we want to go to Mars, we have to stop aging. Okay, we'll never get to Mars if we don't stop aging, because we'll get cancer, cardiovascular disease. We're not coming back. So all those people there that are doing those 20-minute round the world, if they're really going somewhere, they have to stop aging first.
Yeah. Well, in going to Mars, you have to be able to deal with the radiation, because that really promotes aging. That's for sure. Yeah. So a next question is, can patients request metformin from their physicians? Is there a good way to go about this? Do most doctors know about it?
Yeah, that's a great question. So one thing, if you're older than 60, you have like 30-40% chance of being pre-diabetic. It's determined by a test that's called hemoglobin A1C. And if you're pre-diabetic, you ask the doctor to do hemoglobin A1C. If you're pre-diabetic, you tell the doctor, I need metformin. The doctor wouldn't argue about it. There was a trial, the diabetes prevention trial, that showed that people on metformin have 30% less chances of developing diabetes. They will give you metformin. During the COVID, where I was so concerned with family and I felt that everybody is at risk, I started doing something else. I have 2 articles that were published in Cell Metabolism, one of the best journals, that are talking about one of the clinical aspects of metformin and one of the aging and the hallmark aspects of metformin. And so what I do, if people ask me, and I don't prescribe metformin to anyone because I'm leading this study, so I don't want to prescribe metformin, but I tell them, show those papers to your doctor. Now, one of 2 things will happen. The doctor will read the paper and will say, wow, I totally missed it. I should take metformin. I should give to my patients metformin. The second scenario, the doctor will say, I have no time for this bullshit, but you know what? If they want metformin, I'll give them metformin. It's a safe drug. And it's 100% like that. Nobody came to me and said I didn't get metformin. So this is our secret. This is between us.
Another question is, do people age faster now in more stressful times than they did 50 years ago?
It's commonly believed that aging has been delayed by a lot, okay? Not equally among others, but aging has been developed, and everybody will tell you, like I told you in the beginning, that my grandfather died, was 2 years older than me. I look so much younger than him, okay? And I think that's what people realize. We look much better. Our aging has been delayed because we did make progress with the environment. We did make progress with exercising and with food. And true, we had many trade-offs. We're not doing everything right. But overall, health span and life expectancy have increased through 100 years now, starting with water and surgery, immunization, surgery, right? All that have increased our lifespan significantly, but also it changes the phenotype of aging, okay? We don't look as old as we used to look. That's what people will usually tell you. Their efforts to try to make it more objective, okay? There, for example, cameras and AI that will take your picture and look at, your skin and your creases and stuff like that and give you your biological age, and will try to see how are you compared to your parents from their pictures or something like that. But I think overall, look, stress, by the way, stress, there's a term that is adopted to aging called hormesis. Stress upregulates our ability to be resilient and to sustain harm. Exercise is nothing but stress. Believe me, exercise, you have lots of oxygen damage, you have inflammation, you have other things. But we know that exercise is very good. Exercise is example when you get into stress for an hour and it has good effects. So stress is good when it's not chronic. When it's chronic, it kills you, okay? Yes. So just to make a point, a lot of us are stressed. The question is, can we chill? Can we relax?
Another question is, how important are supplements like NAD plus precursors in terms of preventing aging and presumably working through modification of your epigenetics and things like that?
Right. So, the one thing I always start by talking about supplements is that if you buy supplements, it's good for the economy, okay? And it usually does no harm. But the answer is we don't know, okay? And specifically in NAD, we cannot measure it. We haven't shown that this NAD is getting in. We haven't measured that there's an increase in NAD, and there's no clinical studies to show any benefit. Maybe there will be, but there hasn't been really clinical studies like that. And it's really amazing because all the labs, there are a few labs that are really looking at NAD, and they're giving those NAD precursor, NR, NMN, they're giving them to animals. And the animals are doing better, but when they're trying to prove the connection, they are unsuccessful to prove the connection. So I think the verdict is not out yet. I did take those supplements until I read myself out of doing that, and I'm listening to the new science, and actually some of the science is incredible, trying to see if it's microbiome, things like that. No, it's not.
Yeah.
So I'm trying to look for that, but I think that brings to another thing that I really want everybody to know. There, things can have a promise, okay? But the only thing you know if it works is if there's a clinical study, if they took a group of people, okay, and they had either placebo or the drug and they don't know that, and you measure something objective, that's the only time that you know that it works. The other thing, you can say it worked in animals, doesn't mean it's going to work in humans. You can say, but it makes sense, it has a promise, it has that, it's not dangerous. You can justify anything you've done, but you have to know, if you really want to know the truth has to come from clinical studies.
Yeah. So let's say that rapamycin and metformin work beautifully as anti-aging drugs. I think a fascinating question is, when should we start giving them? What age?
Yeah, that's really a good question, in particular because our study on metformin, we're doing a taming or targeting aging with metformin. We're taking 3,000 people between the ages 65 and 80, and we hope to change their whole, placebo control and change those cluster of age-related diseases. So if the study is successful, all we would say is that those people were over the age of 65. But that doesn't mean that it's not better to start earlier, okay? And most of the study that I told you about metformin actually have started at around 50 years old. So I'm pretty comfortable in saying that maybe the age for metformin is 50 years old. On the other hand, there's other drugs that are called senolytics. They are taking those old senescent cells, zombie cells, and killing them. And in animals, that improves health span quite dramatically. But, you have to be, when you're 40 and 50, I don't think you have enough senescent cell to have an effect. It's really when you're 80 that you have senescent.
Absolutely.
And as I said, with the Peter Pan scenario, right, if we want to change the epigenetics, we have to start at age 20. So I think those things will eventually be clear. But
do the drugs work as well on women as men? I mean, often we don't do enough studies of women, and we don't know.
Absolutely true. And in fact, we know there is a program in the NIH that's called ITP, the Intervention Testing Program. Any one of you can suggest a treatment that you think will change aging, and if they choose this treatment, you'll be an author on this paper. But what was interesting with the ITP is that a lot of the drugs, not metformin and rapamycin, but a lot of the drugs were sex specific, were either good only for male or only for female. And even rapamycin and metformin are not exactly similar in male and female. But one thing is for sure, when you give both of them together, then you get the largest extension in lifespan, 24%, those drug combinations. But the sex effect, we have missed it. It's important because we know that women live 4 years longer than men, and it means something in the biology, and there'll be drugs that will work on men and not women, as there are now, by the way.
Well, Nir, I think we have to close up, but in closing our conversation, I'd like to say to you, I think you should take all of the possible anti-aging agents you can, because we'd like to keep you around for another 50 years to be able to come back to town hall and tell us how the science of aging has advanced. So I want to thank you for a wonderful, invigorating, stimulating conversation, and thank you so much for joining us at Town Hall. And I suspect someone is going to step in and take over for me now.
And Lee, I'll come back if you take those medications too, and we both are doing it together.
We'll go off into the sunset together, getting younger and younger. How about that?
Right.
Yeah.
Dr. Hood, thank you so much for leading this conversation. Your warmth was very inviting, and it made this topic that's kind of hard to, digest very, very interesting. And I really enjoyed myself. And Dr. Barzilai, thank you so much for being here. I know it's late where you are, but we're very lucky to have you, and this is very important to hear. So thank you so much.
Thank you, guys. It was a pleasure.
Yeah, and to our audience at home, remember to pick up a copy of the book from our partner bookseller, Third Place Books, and that link can be found in the chat. Thank you, everyone, for tuning in tonight, and from all of us at Town Hall, have a great night.